So in this video, we'll be covering this structure of epsilon delta proof. So as you can see, this is no longer a real number. This is now infinity. So how do we prove this? I'll be using this one as an example. Okay, so first off, we should write the definition. And this time I'll actually run through the definition because it's a little different compared to normal epsilon delta proofs. So we know the normal one is this, right? This is the normal epsilon delta proof. Since this is coming from the right, we can remove these absolute values. This I will cover more on a later video where I'll be covering this form of a limit with plus, and of course as a goes to x goes to a from the negative side. For now, just take my word for it. It should make intuitive sense, but I will explain more in depth in a different video. So if this is our normal epsilon delta proof where it approaches L, we want it to approach infinity. In other words, we want this function to be arbitrarily large. So for any value that we choose that's greater than 0, we have to be able to find a delta where this is true, such that the function is greater than the arbitrary large value we did. And it's a good practice not to use epsilon for this case. Epsilon is usually talking about when the function does approach a single point. This time we usually use m, which I guess it's just convention at this point. So we can say as for every m, and instead of greater than 0, we can say any real number. We could also say for any m greater than 0. This also works, but I think it's common practice to use for every real number. Then we can say there exists a delta, right? This is all the same. Now, since it's 0, we don't have the minus anything. We have this. And we want this function, 1 over x squared, it should be greater than m, right? Because we're basically saying for any arbitrarily large number, right? We can find a delta. In other words, we can find, like, in this case, it just means we can find a delta greater than x where this is true. And if we can prove it for every real number, that means we've proved it goes to infinity, right? Okay, so this should all make sense. So this is our want to show. Want to show. Now, of course, we want to just set up our proof real quick. So let m in the reals. Now we want to take a delta as something, right? And then we have to define x and assume the first part of our condition. And we have to prove that 1 over x squared is greater than m. Okay, so let's do a rough work. Actually, this rough work isn't nearly as hard as most epsilon delta proofs, actually, which is kind of interesting. But it is very different, right? Because we have all real numbers, and this is definitely not the same as epsilon delta proofs. Okay, but let's see. All right, we know this is true. We want to prove this. In other words, if we multiply both sides by x squared, right? We're also trying to prove this. This should make sense if we multiply each side by x squared. If we can prove this, then we've proven this. So we're just seeing, all right, what can be proved? Okay, what if we divide each side by m? Okay, so now we need to prove that. And now if we square root both sides. Okay, so if we can somehow prove that x is less than 1 over root m, then we've proven our statement, right? Because we can just rearrange to get the other way. Okay, so we want to choose a delta such that this will be true. So if our delta was less than or equal to 1 over m, then would you agree that this would be true? I'll just let you just think about that. if we set our delta as 1 over root m, then we would know, obviously we know that x is less than delta, right? And this would also mean that x is less than 1 over root m. Oh, wait, but this is exactly what we need. So that was pretty easy. Okay, so let's do that. 1 over root m. Though we have to be careful here because m can be a negative number. So we do have to choose the absolute value of m. Otherwise, this proof will break because we can choose an m that is negative. You'll see many of these proofs involving for every m greater than 0, which avoids this problem, obviously. But it is common practice to have m be defined on the real number. Okay, so we have the absolute value of m. So now we can actually do our proof. So we start off with, here we can write like a little statement here. Therefore, x is less than 1 over the absolute value, absolute value of m, which implies x squared is less than 1 over absolute value of m, which implies the absolute value of m is less than 1 over x squared, right? Which implies that m is less than 1 over x squared. And then we see that literally just proves our rule. So therefore, m is less than 1 over x squared. And that's the end of our proof. You could also, what's better convention? I guess you could, we can say that we can conclude and then we can just say this, I guess. Therefore, like it's either way, you just need this part, right? So actually, this proof is actually pretty simple compared to other ones. Yeah, I mean, the key takeaway, because this is actually easier than, in my opinion, compared to an absolute delta proof. But the key takeaway is defining m instead of epsilon as just any real number.